So object detection means classification and localization. Two. Actually, we are doing two tasks here in one go. Okay. The classification means whether it is a car or a bike or a person, we need to classify. Then where exactly it is present, we need to actually do. We need to identify. We say this as bounding box. Okay. To actually do this, right? To classify an image, whether it is a car or a human being or a bike, what we need, how the data set should be. I need to classify. If I get a photo, I need to classify whether that photo is a car or a bike or a human being. What should I do? From the step one to from data collection to prediction. Can you tell me the flow? Sir, even if it is wrong, that's fine. Please attempt.
Okay. So data collection, pre-processing. After that, like image processing.
Image processing means you convert image to numbers.
Numbers. Numbers, and also like convert into. After that, we are creating that layers.
Labels. Layers. Okay. Deep learning layers.
Yeah, deep learning. I'm talking to.
But what about data set? Data set pre-processing is done. Is that enough? You have 10 bike images, 10 car images, and 10 human being images. You converted them to numbers. Will you be able to do classification model?
No, sir. We need to like take some classification, right? Decision boundary kind of thing. We need to find out the frame exactly.
No, not frame. I am not talking about bounding box. I am just talking about just classification model. See, when you worked with this digit recognizer data set, what you did in data preparation?
We are labeled, sir.
Labeled data, right?
Yes.
So that labeling is the very crucial thing. See, I took the data, then labeled it, right? And then I started, doing whatever, right? So even when you are doing this object detection thing or object, whether it is a car or a bike or a human being, whatever classification you want to do, you need to convert data. You need to have a labeled data set. Okay. So you label the data. So you collect data, you convert it into pixels, you label the data, then you will be able to do classification. Okay. Similarly, to do a bounding box also, for each image, you need to have the bounding box coordinates. Okay. If you look at this data set, right, there is a handwritten digit converted to pixels, and there is label, right? This will be able to do classification. With this data set, we'll be able to build a classification model. If you want to do bounding box also, for this particular image, you should have bounding box coordinate also as labels. Got it?
Okay, sir.
Right? Multi-label, multi-output classification, right? So multi-output classification it is. So you'll have multiple y variables. One y variable belongs to which class it belongs to. Other variables, other y variables belong to the coordinates of where exactly the picture is, located in the given image, right? Where exactly the object is located in the given image, right? So that is localization. To do this activity, the data set should be prepared like this. Okay, I am just trying to give you a high level view of where we are going. Okay, so this is a image, and then in this image, do we have a car? Yes, we have, right? Basically what we did is we splitted this image into nine nine boxes. Okay, I'll show this later, but see this here. So do we have a car in this? Yes, we have. That's the first label. Y label for one record it is. Sorry. Y label for one record it is. Where is that? Y label for one record. Okay. This is whether object is present or not. These are all the coordinates of the, sorry, these four are the coordinates of the object. Okay, and these three, right, whether an object is present or not is first variable. Which object is present? Car, bike, or human being. Wherever you have one, that object is present. Okay, this is now 0.5, 0.5, 0.762, 0.76, right? The 0, 0 starts here, the 1, 1 starts, ends here, right? And then the middle of the picture is going to, middle of the total image is going to be 0, 0.5, 0.5. Fortunately, for this image, the origin of the image also actually came 0.5, 0.5. Okay, and then this is height, how much height it is and how much width the image is. This is one way of specifying the coordinates. Other way is like from origin how much width, from origin how much height. That's another way. Okay, so two ways of specifying the y variable are there. So you should have the y variables here. If you have a y variable like this, right, this variable, it's a classification problem. These three are classification problem. These are regression problem. Got it? They are numbers between 0 and 1. Now the model need to predict, or you can take classification also there. To you will be predicting the probabilities. But the y cap, that whole manipulation may get distracted. So you this is like this is a classification model. But the loss function is kind of the regression loss function only. Are you getting this y variable concept? How to label the data. To do object detection, how to label the data. Do we need to do all this manually? No, we have tools. I'll show you.
Okay, sir. Okay. And so second thought 0.5, 0.5, this is like to find out that image centering point, right?
Image center. That whole
Yes.
whole picture center it is.
Yeah, pictures.
But fortunately, in this image, right, the car also fell on the exactly in the center, and that that whatever it looks like the car's center. I would have taken a different whatever.
So this is common for every image or what? 0.5, 0.5.
No, if object comes a little this side, right, the number will change.
Okay.
Origin number will change, and origin and offset. That there the origin is going to be very useful. Origin and offset we call it. From origin how much height, from origin how much width. If you try to specify here, then it is like offset we call it. Okay, you got it right. To do object detection, you need to have the y variable like this. For all the images, you should have y variable like this, and then you train the model, and the model will, if you pass a new record, it will actually identify the object, classify the object, then do a decision boundary also. Okay, so that is the basic concept of object detection. Now we will go into the details. Okay, so before we do object detection, right, I'd like to show different approaches of doing object detection and the problems with it. Okay, if you would like to detect dog in this picture, right, classify if dog is present or not, and draw a bounding box. If you want to detect means what, you want to classify in this object whether dog is present or not, and then draw bounding box in it. In below image DNN model, with no CNN, there are three steps. If you want to do a DNN model, we can do it. For object detection, right, we can do DNN model, but the way we have to do it is build a dog classification model with closely cropped images of dogs. Right, you crop this. Right, you take maybe 1,000 images, maybe 10,000 images where dogs are present and dogs are not present. Okay, and then you take the 10,000 images and crop them closely. Give me 1 second. Okay? Give me 1 second. Okay, so sorry. So you need to crop the images, closely cropped images you need to take, and then do a classification model, right? Dark classification model, and then take this picture and crop the image, crop that picture into the same size, when you actually did the dark classification model, right? You cropped images, right? Like that, you need to cut this, first cut, second cut, third cut, like that. You need to cut and pass it to that model, this model. The first model you built, right? Classification model, right? So you need to pass that where you find that, wherever that model says, no, the object is there, you need to take those pixels and then you need to do a bounding box there. That's the way. Did you get it? The clear, idea of how to do a object detection model using DNN? Theory it is. We will not be doing this because this is not efficient. I'll tell you all those things. Any questions there?
No, sir. Clear, sir.
Okay, so simple, right? You have a classification model. The classification model, uh, wants the input in some dimension. So you are cutting that image into that dimension. This is called a sliding window classification. Okay, sliding window, or we crop, we are sliding, right? And then we are passing it to the model, and model is trying to predict where the object is, right? So that is without CNN how to do. But in CNN you are doing, we are already doing that sliding window stuff, right? In CNN the filters are actually sliding, right? If your filters are intelligent enough in identifying an object, classifying an object, you just do CNN, it automatically does the sliding and it identifies. No need to crop manually and pass it, right? That's the advantage of CNN.
Yes.
Got it?
Yes.
Let's see this here. If we would like to detect a dog with CNN, right? Classify if dog is present or not, right? And draw a bounding box. In below image with CNN, there are two steps actually, three I doubt. Build a dog classification closely cropped images, classifying with all CNN layers. All CNN layers. This we never saw. Today I am going to show you that. Okay. So if you look at this CNN, right, in these CNN layers, in CNN networks, in the end, we actually have these DNN layers, right? I am saying all CNN layers here. Right? That's the new thing. All CNN layers, right? Feed the image to classify, right? Down bounding box. So let us try to look at that example pictorially. See, right, with a CNN DNN model that actually does image classification. Okay, image classification and bounding box. Suppose that I should have kept one more circle here, right? So first one to classify whether the image is present or not. If the image is present, then bounding box. Maybe we are doing bounding box only. If image is present, we are doing bounding box. If not, we are not doing bounding box. Like that it is. Okay. You took an image, right? You took many images of 14 by 14 by 3. Right? What is 14 by 14 by 3? The closely cropped dog image. Okay. The closely cropped dog image 14 by 14 by 3 you are taking, and then you built a neural network to find out bounding box. Okay. So this, suppose that is this network. Okay. Now if you have to apply this onto a bigger image, you will not be able to do that. Okay. So here, yeah, this is fully seen. So here, right, there is a I need to draw this and explain. Give me one second. Give me one second. see this. Take a screenshot. Okay, so I said that there there are some closely cropped dog images. Okay, there are some closely cropped dog images of this dimension. Okay, this is a dog. Right? This is also a dog. This is also a dog. This is also a dog. Right? Like that. So there are many dogs. Okay, we are passing those and then training a model. Now suppose that the model is trained successfully. Okay, so if you look at this, I am applying 5 by 5 filter. Right? The 5 by 5 by 3 is the dimensionality, right? Because number of channels in the previous layer are 3, we get 3 here, right? 3 channels. When you apply 16 of them, the depth is going to be 16 because for every filter you will get a 2-dimensional array, right? That part is clear, right? Any questions there? I'm actually going backward, right? So like that you will get channels. And again I said filter size 2. It is 2 by 2 by 16. Right? 2 by 2 by 16. And I am applying 16 filters again, right? Same number of. So you will get 16 depth. So when you apply 2 by 2 by 16, right, you will get 2 by 2 by, it's like n minus f 2p, that formula is there, right? If you calculate, you will get 5 by 5. Now what I did, I flattened it. I got 400 values, and there is a dense layer, and a softmax I am trying to predict. Okay. So that is maybe you are trying to predict 4 different classes: dog, cat, horse, and maybe elephant. Okay. So you passed dogs, cats, and maybe this is dog, this is cat, this is elephant, this is cat, this is dog, this is like that you read. Okay, many records you passed and you trained. Now the model is working good. If you want to use this model to do object detection, object classification, don't talk about detection now, just talk about make things simple, right? Multi-class classification. Okay, multi-class classification you want to do. Multi-label. Give me 1 second. Let me think. Yeah, multi-label classification. Do you remember what is multi-label classification? This is multi-class. Yeah, this is multi-class only. Sorry, not multi-label. If you want to do multi-label, right, you should be doing logistic regression nodes. 4 logistic regression nodes are there. It becomes multi-label. This is a softmax, right? Is multi-class. Okay. So it is going to give you one outcome, one outcome. But if you have 4 binary class models, right? If you have 4 logistic nodes, you will get 1 0 0 0 like that. For 4 y caps you will get, right? If you have the y cap, y is like multi-label. Then do you remember what is multi-label? What is multi-label and multi-output classifications? Yes, no. Keshva, your video is on. Your video is on. Yeah. So, do you remember multi-label, multi-output classifications? Narayan garu or Srinivas garu?
Multi-label.
No. Multi-label classification means, right? You have x1, x2, and so on xn, and you have y1, y2, y3, right? Maybe some y number of y variables, and Multi-label, you will have 0 or 1, right? 1 or 0, right? Every record will have either this image or this image or this image or this image is present. That is called as multi-label classification. Multi-output means there will be a number here. In Y1 there will be a number, right? There will be multiple classes there, right? This will have, maybe 1, 2, 3, 5, like that, maybe 5, 6. Every Y variable will have more than 2 classes present in it. That is called the multi-output. Okay, you can do that also with deep learning. Maybe I'll talk about that tomorrow. But this particular network is trying to identify whether a picture has got a dog, cat, horse, or elephant. Only classification model. Okay.
Multi-class.
Okay, if you multi-class. Okay, multi-class. If you want to use this network to predict, what you need to do? You take the picture and convert it into 14 by 14 by 3, or crop the image and pass it. Then only it will work. Okay. So why not? Why will this not work? Even though this is a CNN model. What I said, CNN model actually can do sliding, right? Let me try to take another cover. CNN model that's a picture of a new whatever, right? Generally, what this CNN model should do, this model should do, it should actually do not that one. Sorry, this one. These numbers are the network, right? So that one actually should do 5 by 5 and 5 by 5 and 5 by 5, 5 by 5, 5 by 5, like that. It should actually do, right? Right? And then it should actually produce these whatever, right? But what happens is, if you do that, this is 14 by 14. When you apply 5 by 5 filter, and you are getting 10 by 10. If this is 28 by 28 by 3, right? If you do sliding window, what happens? You get a 14 minus n minus n plus 2p minus f. 2p is 0 minus f is 10 plus 1, right? Is going to be what? Sorry, this filter size is 5, right? Right, n minus f plus 1, because p is 0, s is 0, s is 1, no need to consider that. So it is 10 by 10 by 16. But on a 28 by 28 by 3 image, if you apply for this filter, what happens? What is the output size? What is the output size? If you apply this same filter, 5 by 5 filter, on a 28 by 28 by 3 image, what is the output size?
28 minus 5.
28 minus 5 plus 1, right? 28 minus 23 plus 1, 24. This is 24 by 24 by 16. Okay, so let me put it neatly. Okay. I generally write very 24 by 24 by 16. Now I apply two filter, right? 24 minus 2 plus 1 is 22 plus 1, 23 by 16. Okay, till here it's okay. Even though the input image dimensions are different, the CNN was able to handle. Do you agree? Do you agree?
Yes, sir.
Right. Now the problem comes. If you see the dense layer, it has got 400 nodes. Okay, and the 400 inputs basically, right? 400 inputs basically, right? So 5 by 5, 25, and then 16, and even I took nodes also 400. So 400 inputs sent to 400 nodes. Now the dimensionality changed. 23 by 23 by 16 means it's a huge data. When you try to send that to this dense layer, will that work? For dense layer, will it work? If yes, no, why? If no, why? I'm just making you think a little bit. If the input dimensionality changed and you passed it into dense layer, will it work? So you are predicting on a 28 by 28 by 3 image. You built a model on a 14 by 14 by 3 image, and you are trying to predict it on a 28 by 28 by 3 image. Will it throw error here?
Yeah, I think so, sir, because it is 400 nodes only, but we are passing almost, if you're 23, that means 8,000 or something.
More, lot of. So you know, when you look at the neural network of a the DNN, it will actually form an equation with the number of parameters, number of input variables and the parameters, right? So your input is high. It is like linear regression. It is like linear regression. You know, while training model, you pass 10 features, and while predicting, if you pass 20 features, it will throw error saying because the equation can accommodate only 10 features, right? Beyond x11 it cannot handle, so it will throw error. So because of having a fully connected layer in the network, we are unable to, you know, make predictions on a different sized image. Okay, to solve this problem we should rely on fully connected deep neural network, fully convolutional deep neural network. Where is it? Fully convolutional neural network. Right, fully convolutional neural network. If you look at you know, this one has got fully connected layers at the end. This one has got, you know, even at the end also convolutional layers only we have. These are all convolutional layers only. Okay, this is called as fully convolutional network. This is convolutional neural network. Okay, this is called as just convolutional neural network. This is called as fully convolutional neural network. Did you get the difference between these two? I'll show you the advantage here in a moment. Did you get the difference?
So here you applied for every image, right?
You know, here also I applied
Filter.
convolution only, CNN only. In the end, let me show you the difference now. Okay, so if you do a fully convolutional layer, right, fully convolutional network, that will not have that problem, whatever problem we faced before. You know, in this the problem was, you know, the input was too high, and the linear model, these dense layer cannot handle because the equation is not sufficient. If you do that same thing on this side, if you do the same thing on this side, if you passed a 28 by 28 by 3, 28 by 28 by 3 picture, you are applying, you know, 5 by 5 by, you know, 5 by 5 by 3 filter, that's going to give you 24, right? 24 by 16. Now you apply two filter, right? It's going to be 23 by 16, right? Now you apply 5 filter, right? It is actually sliding simply, right? 25 minus 5, 23 minus 5 is 18, 19 by you took 400 filters here. Okay, is that a mistake there? Yeah, this is a beautiful thing. Give me 1 second. Okay, I did some mistake here. Cooling layer, this is convolutional layer. Then this is pooling layer actually. This is pooling layer. 2 by 2 by 16, right? 2 by 2 by 16. 2 by 2 by 16. Pooling layer is going to give me slide 2. Should I give slide 2? I think this is 2 here. Do you remember the formula? Do you remember this formula for pooling layer? N minus 2p plus f divided by s plus 1, right? Is the formula right? I'm just checking. N minus 2p plus f divided by s plus 1, right? So if the stride is 1, what happens here? 10 by 10 by 16, n is 10, minus 2p is 0, plus f is 2, sorry, yeah, 2 divided by 1 plus 1 is going to be, what the heck, n plus 2p minus f, sorry, n plus 2p minus f, right? N is 10 plus 2p 0 minus f is 2 divided by 1 plus 1. What will happen? It is 9, right? 9 by 9 by, the stride is 2, the diagram is wrong, right? If stride is 2, then what happens? It is divided by 2, right? So it's going to be 4, 4 plus 1, 5. This is 4, right? Plus 1, 5, right? So that stride is 2 here. Got it? There is a mistake in the diagram. Okay. So if I do the same, the max pooling on this, right? The pooling layer, then what happens? 24 minus f is 2 divided by 2 plus 1 is going to be 22 by 11 plus 1, 12 by 12 by 12 by 12 by 16. Okay, you should calculate these. It will actually make us more confident. It's not really needed, but while working, right, you will get more confidence. I know, and that's the feeling it actually gives. Okay, so 12 by 12 by 16. Okay, now what I did, 5 by 5 by, the filter is 5 by 5 by 16. Here, if you look at this, 14 by 14, you applied 5 filter. 10 by 10, you applied max pooling with 2 stride. It became down. It came down to 5 by 5 by 16. If you see the filter size here, 5 this is. Okay. Now, the filter size is what? 5 by 5 by 16, right? The filter size is also 5 by 5 by 16. When you multiply a 5 by 5 by 16 matrix with a 5 by 5 by 16 matrix, what you get? Element wise multiplication. See, the convolution, sorry. Convolution. If you do, suppose that there is a matrix 2 by 3, 2, 3, 4, 5, and 1, 2, 1, 2. Right? There are two matrices. Right? You are doing convolution here. What is the output of convolution? Can you tell me? Can you tell me what is the output of the convolution?
2, 6, 4, 10.
No. Convolution I am asking, not the element wise multiplication. Plus 3 into 2
yeah.
plus 4 into 1 plus 5 into 2. Right? 2 plus 6 plus 4 plus 10. 10, 22 is the output. When you multiply two same dimensional matrices, when you do convolution, not multiply, convolution of two same dimensional matrices, you get one number. Got it? Got it? Any questions there?
No, sir. Got it, sir.
Got it. Now what happens here, sir? Tell me. 5 by 5 by 16 is the output, and I have taken 5 by 5 by 16 as the filter also. When you apply filter, one filter, what happens? What you get? When you apply one filter, will you get a matrix or a single number? Matrix or a single number. When you multiply this matrix with this matrix, or when you do convolution of this image, this output with this filter, what you get? One number or multiple numbers?
One number.
One number only, right? Here you see, when you do convolution of two same dimensional matrices, whether it is 2-dimensional, 3-dimensional, it doesn't matter, you get one number. So I have taken 400 filters, then you will get 400 numbers. Now first filter will give that number, second that number, third that number, fourth that number. This is like flattening only, right? When you do flattening, what is happening? In the previous fully, a convolutional neural network with with dense layers, what you did, you actually did flattening here. When you flatten, you are getting a one-dimensional array, right? One-dimensional vector. But here you get a three-dimensional vector with 1 as depth. 1 by 1 by 400. Right? 1 by 1 by 400 you get. Right? This is like flattening only. Flattening your network. When you applied 5 by 5 by whatever, right? You got a flattened vector, and then you are applying again 1 by 1 by 400. This is again 1 by 1 by 400. The outcome is also 1 by 1 by 400, and you are actually you have taken the filter also 1 by 1 by 400, and again 400 filters. What happens? Every time you apply filter, you get one number, 400 numbers. Okay. Now you are applying 1 by 1 by 400, 4 filters only. 4 filters only. What you will get? 4 numbers. One number, second number, third number, fourth. First filter, second filter, third filter, fourth filter. Did you get it? Fully convolutional neural network. Did you get it?
Yes, sir.
Right. This is the trick here. This is a trick here. Okay. I'll update this sheet, this whatever the network, and then I'll upload it. Right. That's the trick. So you are actually, this is prediction basically. This one you will pass it to the cost function, and it will try to adjust the weights. Okay. So with all convolutional layers, you can build a classification model. That's the key. What is the advantage of doing it? I'll show you in a moment. Right? What is the advantage? So now you built a model with 14 by 14 by 3. You are passing a 28 by 28 by 3 image, right? In a on a neural network where in the middle you have the fully connected layers, it throws error because the dimensionality of input is not matching. But in a fully convolutional neural network, it will not throw error. It will actually execute, but the output will be a bigger one. No, that's the point I want to explain. The output will be a bigger one. See this here, 24 by 24 by 6. I applied the pooling. It became 12 by 12 by 16. Now I am applying 5 by 5 by 400. 400. This is actually production. Prod. You passed a new record. You are actually doing 5 by 5 by 5 by 5 by 16, right? 5 by 5 by 16 filter you apply on this. What is the output there? You are applying 400. What is the output? 12 minus 5 plus 1 is how much? 12 minus 5 is how much? 8, right? 9, right? 9 by 9 by 400. You are applying 400 filters, right? So you get a 9 by 9 by 400. Okay. Now you are applying 1 by 1 by 400 filter. What you will get? 1 by 1 by 400 filter you apply. 9 minus 1 plus 1 is the dimensionality. 9 by 9 by 400. Okay. Right. Now you are applying 1 by 1 by 400, 4 filters only. What will come? 9 by 9 by 4 you will get. Okay. So you will not get error, but you will get a bigger matrix. Here it is 1 by 1 by 4, right? Because it's a 14 by 14 by 3 image. You passed a 28 by 28 by 3 image, you got 9 by 9 by 4. That means what? It's a 3-dimensional array like this. Let me draw this. Oh my god. What I did? Control Z. Okay. So this particular output, right? It is like this. You see, you should think along. You should think along. Then only you'll get it. So that's first one. That's second. That's third. And then there will be 9 by 9. 9 by 9, whatever. So why 9 by 9? The model is actually trying to see whether there is a cat or a dog or a elephant or a horse present. In the second cell, the model is trying to predict whether dog, cat, right? In each cell, it is predicting. When it is sliding through, it is actually trying to predict 81, places of the image. You know, this is 28 by 28 image has got 81 places, right? According to this particular filter, right, there are 81 cells in the picture, and each cell, do we have all 4 classes or not? That's the prediction it is trying to make. And the model will actually predict, you know, whether there is a dog or a cat or a, you know, elephant or a horse is present in a given 14 by 14 by 3 area, right? This is a 14 by 14 by 3 area. Again, there will be a overlapping 14 by 14. So there will be 14 by 14 by 3 areas. 81 areas are there. All 81 areas, it is trying to predict whether one of these objects is present or not. Got it?
Yes,
I'll
sir.
show code example in a moment. Got it?
Yes, sir.
This is the basis of object detection. Okay, we will look at YOLO algorithm at a high level, and building object detection model is very easy. Understanding theory is difficult. Okay, understanding theory is very difficult, but building model is very easy. Don't be scared. And you know, if needed, right, I'll reiterate the same concept tomorrow. Right. So if needed, right, tomorrow morning when I start class, right, you know, just let me know. We need yesterday's class also. I'll just show you. Okay. So I'll show you the difference now between a neural network where fully connected layers are there and how it is throwing error, and a neural network where you have all fully, you know, convolutional neural networks. Okay, let me try to show that code. So this was actually, you know, I explained this concept almost 2 years back and asked students to build it. They never did it, so I did it in the last batch. So similarly in NLP also, I'm going to give you one task. Somebody does it, that's good. If not, right, at one point in time when I get time, I'll actually do it. So we are trying to understand fundamentals of object detection. Okay.
Yes, sir.
Okay. So now for digit recognizer, I did it. You know, fully convolution and on big image. Why it says, try to see this. Okay. Give me 1 second. I did it long back. I need to have a look at it. So I did a lot of things here. Lots of stuff. Yeah, this is the basic for OCR. How OCR works is this is the, you know, this is the basic thing. Okay, this is the fundamental thing and how OCR works. So let me explain this today, and tomorrow again I'll explain. Okay, so because there is a lot of stuff happening here. So before going here, right, I will actually go into this. Big image, I said that's where. Okay, that's the big image thing. So maybe I need to change the name of it. So my idea is, right, this scenario I try to simulate. So 14 by 14 by 3 image is the small image where I built a classification model, right, like this, a classification model. And then I have taken a bigger image like 28 by 28 by 3, whatever, and then trying to use this network to make prediction. I'll show that it throws error. Okay, I said it will throw error at here, right? Till here it will run fine, but here it will throw error, right? That is the example, this one. Okay, so I have taken the digit recognizer, right? I converted that into 28 by 28 by 1, 28 by 28 by 1, because it's a one dimensional whatever, right? So depth is 1 only. Right? Then I built a convolutional neural network with the fully connected layers. fully connected layers, we call them as dense layers, we call them as fully connected layers. And I have taken softmax, it's a multi-class classification. I built a model, right, and it's working fine. I tried to save this and this is not there. Okay, that's okay. And now I have taken this, where is big image? I did not actually ran it, it will throw error. So I have taken, I have taken some image and then made, try to make prediction. I'll update this code, okay? I'll update this code and show you tomorrow. So it will throw error, when you actually take a bigger image like this. So what I did was I actually built this kind of an image, and then I was trying to, classification model actually was trained on individual image, individual handwritten digit, right? To simulate this kind of a situation, right? This kind of a situation, a bigger image, a small image trained, and then a bigger image and training, I created this picture. Okay, and then I was actually doing the sliding window. So handwritten digit it will try to identify. So when I tried to do that, right, you see, this is how I got. So I ran it, it identified this as 9, I think. Many times 9, many times 7, right? It actually had many blocks there. So 85 by 85 is the dimensionality there, and we have got, see this, yeah, it actually predicted right. See 5s, right? Then 7s, then 2s, then 6s, right? 2s, 7s, 5s, right? So it was actually, it's a OCR thing actually, okay? Fundamental of OCR. So let me, run through quickly so that I'll also get a, kind of vision on what I did. Okay, so I have taken the picture, then tried to show, and then did some normal scaling and all that activity. And target variable I changed it to, I don't know why, to categorical. And then I built a neural network with all convolutional layers, no dense layers. See this, right? All convolution, con 2D, 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 all convolution. Okay, I built a model, right? I built a model on 28 by 28 by 1. The input was 28 by 28 by 1, like in 14 by 14 by whatever, right? Right, like 14 by 14 by 3. I took 28 by 28 by 1 and built a model. I trained a model. Okay, the model worked well. Image generator, whatever, and then I trained it. So I have this many layers. So what I'm doing is I have the same network I am using. How to use the same network? That's the big question, right? So I'll close this. So what I am trying to do is I have to use the understanding I made on this network on a bigger image. So what I need to do is I need to copy the filters, right? I have some filter here which was trained on for 40,000 images. I have some filter here which is trained on 40,000 images, right? These all filters I need to copy. That's what I'm doing here. I am copying the filters. So before copying it, right, I am creating a network. Okay, so network is like, input is 112 by 112 by 1. Original model was trained on 28 by 28 by 1. I am trying to make prediction on a bigger image. So I am actually creating a neural network here, right? Neural network with the filter size 3, 6, 12, 24. See this 3, 6, 12, 24, 48, 96, 192, 384. Same dimensions. Okay, same dimensions I have taken. The network size is same, right? Everything is same, but input only changed. Okay, input layer changed. Now, to actually make this model get the intelligence of the 28 by 28 by 1 model, I need to copy the weights. How do I do that? See this here. The OCR model variables, HR model, right? The initial model, that 28 by 28 model variables, I am actually, looping through by zipping them and then assigning the values of B to A. Did you understood this code? Did you understood this code? Why am I doing that?
No, so what is the OCR model, sir? Can you show me the OCR model? Where is that?
What is OCR? Can you tell me what is OCR? Optical character recognition, right?
Recognition.
In an image, you want to identify whether there is a 5 or 2 or 3 or 7, whatever, right? So
Yes,
that
sir.
is optical character recognition, right? So to
Yes,
do that, what you need to do? You need to train your model on individual handwritten digits first. Okay?
yes, sir.
And then run it through the model in a sliding window fashion, right? That
Sir.
individual image classification model, you need to run it like this. Run here, 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 like that, and see whether the object is there or not. Got it?
Yes, sir.
Right? So what I did here is, first I took handwritten digits and built a model. Closely cropped images, dog image, cat image. That model I built. Okay, that is this model. Okay, HR model I said, I don't know why HR.
Model. Okay.
Horizontal, or I don't know, maybe I have to change this name. Okay, this is completely indigenously built by me, no copy code. Okay, so here I built that individual image, individual handwritten digit model. Now I need to run this through the image, right? So the image is, the OCR image dimensionality is 112 by 112. This is till here it is model. This is the OCR model. So I have created a model. I called it as OCR model, right? And a bigger image, I wanted to run the pre-trained model, the 28 by 28 by 1 model, right? The bigger image model, I am calling it as OCR model because it will work on a big picture. Got it?
Yes, sir.
Right now, what I am doing is, if I have to, if I have to use the 28 by 28 by 1 model, right? What I should do? HR model. I need to copy all the weights. Weights are the understanding, right? All the weights to the OCR model, because OCR model structure and HR model structure are same. Input is the only one thing we changed. When the structure is same, when the architecture of the neural networks are same, you can actually copy weights from one model to another model. This is a very important, very important concept. Nobody will explain this. Okay, got it? This loop, you got it?
Yeah, I got it, sir. This one.
Right. Now this model has got capabilities of 28 by 28 by 1, right? And it has got a bigger dimensionality. What will happen? It will do like this. When you actually pass when you take a smaller network weights and pass it to a bigger image, what happens? It will do, many areas. It will actually identify whether, here we have 0 or 1 or 2 or 3. Here we have 0 or 1 or 2 or 3. Like that, it will actually do a mesh search, mesh search, or you say sliding window classification search. Okay, that's what it did. So I actually took uh, some images, right? Some hmm, row number 1, row number 2, row number 3. I don't know what I did. Okay. I actually created this image. Don't be worried. I created this image. That image, I have to save all these things. I have not saved them. So this image I created, right? Manually I created a OCR, example, and then I am reshaping it, and then I am actually doing predict on the OCR model, right? That actually identified 85 by 85 cells in this 128 by 112 by 112 image. It found 85 by 85, 28 by 28 by 28 by 1 cells. Got it? Got it? No? If you look at this picture, right? How many numbers are there in this picture?
16.
16 numbers, right? But the model is trying to find there are 4 by 4. This is actually a 4 by 4 matrix. We should get 16 numbers as output, but the model is trying to predict 85 by 85. 85 by 85. Number of numbers in that picture. Why is that happening? There are only 4 by 4, but 85 by 85 it is trying to find out. Depth is 10. Depth is 10 means, wherever whichever number the record belongs to, there you will have highest probability. Depth. Okay. 85 by 85 is the number of numbers it is trying to predict on this picture. Got it? It will do more than what is needed. But there will be overlap. In the first slide, it may actually do slide like that. It may find 5. It may slide a little bit and do again. It may find 5. It may slide a little bit again. It may find 5. Like that, right? When it is sliding through, it is finding 85 by 85 numbers, even though there are 4 numbers only. The optimization of finding the 4 by 4 are the models which are there in the internet. I did the core basic model. Okay, so when I actually make prediction, right, I took see this right, numbers probabilities, and then I am actually trying to look at the 10th the depth dimensionality, and then on the depth dimensionality I would have done some whatever, right? So it actually gave me the numbers it found, 8 by 85 by 85 numbers it found, right? On the picture, the 85 by 85 numbers I found. How did I find? Argmax of predicted probabilities in the axis 3. The depth dimensionality I actually tried to see argmax. Then I got 85 by 85. Okay, so it found this many numbers there. We actually have to find 4 numbers only. See this? Almost 4 records, 4 rows, it actually finding 5 only, because it is sliding here only. Sliding here, sliding here, sliding here, sliding here. Again, it just came down and came a little bit here. Then it found 5. Again found, again 2, again 7, again. Like that it is doing. Got it? Got it?
Yes, sir.
Right? That is, that is OCR. How OCR is working, we have actually seen. I even forgot that I built this. Okay. So that's it for today. I think today we had too much. Right?